So hello everyone, we are going to start with the next chapter, which is chapter 8, multiplexing for the week 5. Alright, so let's start with this chapter. I have divided my this chapter into two parts. So in the first part I will cover frequency division multiplexing, what is multiplexing, frequency division multiplexing, and a little bit about time division multiplexing. Then in the next part we will talk about, in the next recorded lecture I will talk about more on time division multiplexing. So let's start with this. Alright, so what is actually multiplexing? We know that the medium, the channel, the link is shared between the various people or the various users. So the process of taking the signals from the users and combining them into as one signal and then sending that one signal on the shared transmission medium is called as multiplexing. So I repeat it again, process of taking or combining the signals, analog or digital, from the various users and combining them into one signal and then sending that one signal, combined one signal, on the shared transmission medium is called as multiplexing. The opposite of multiplexing is done by a device called multiplexer, and the opposite of multiplexing is demultiplexing. Demultiplexing, what it does, it takes the one signal and then separates the number of channels or the number of combined signals into the respective one. So the process of demultiplexing is done by a device which is called as demultiplexer. So multiplexer is always attached at the sender side and demultiplexer is attached at the receiver side. Multiplexing, the technique of multiplexing, just in one word, it is also called as many to one because it combines many signals and makes them as one signal. Demultiplexing is also called as one to many because it takes one signal as an input and then gives out many outputs. So let's read it. Multiplexing allows several transmission sources to share a larger transmission capacity. We need multiplexing because we know that our transmission medium has a limited capacity. There are many constraints on the transmission medium, and moreover the transmission medium is shared among the various users. So we have multiple links on the one physical line. A common application of multiplexing is in the long haul communication, especially in the telephones. Trunks on the long haul communication are high capacity fiber coaxial. So the type of transmission medium that we use for long haul communication, they are high capacity fiber optic cables, coaxial cable, or the microwave links. Now these links can carry large number of voice and data transmission at the same time using multiplexing. And the common forms, what are the different forms of multiplexing? We have Fdm, which is called as frequency division multiplexing. Tdm is called as time division multiplexing. Wdm is called as wavelength division multiplexing. STDM is called as statistical time division multiplexing. So out of these, more commonly we are going to explore Fdm, which is frequency division multiplexing, time division multiplexing, and we will talk about statistical time division also. So let's start with this. So let's start with the frequency division multiplexing. Alright, before going ahead, now one more point that I will like to mention is, in the previous slide is, now when we talk about multiplexing, that means we are combining the signals according to some parameters. Now frequency division multiplexing means multiplexing is done based on the frequency of the signals. So different signals may have different frequency, so they are multiplexed according to, so that means signals of different frequency, carrying different frequency, they are combined together. That is called as frequency division multiplexing. Time division multiplexing is based on time. In this case, a time slot is given to each user. Wavelength division multiplexing, when the multiplexing of the signals is done based on the wavelength. And the last one is statistical division multiplexing. It is actually a form of the time division multiplexing, but it has some more parameters. Alright, so going ahead now, talking about the demultiplexer also. So the multiplexer is connected by a single data link to the demultiplexer. Now what is the use of the demultiplexer? The link is this link is able to carry n separate channels of data. The multiplexer combines means multiplexes the data from n input lines and transmits over a high capacity data link. Now what does demultiplexer does? Demultiplexer will accept the combined or the multiplexed signals and it separates or demultiplexes the data according to the channel and delivers the data to the appropriate receivers or to the appropriate output lines. Why do we need multiplexing? We need multiplexing because higher the data rate, more cost effective the transmission facility is. So for a given application and over a given distance, the cost per kilobits per second declines with an increase in the data rate. Also, most individual data communication devices, they require relatively modest data support. So for example, many terminal and personal computer applications that do not involve web access or intensive graphics, the data rate can be between somewhere 9.6 kilobits per second to 64 kilobits per second. Alright, so we are going to talk about now the further techniques, which is frequency division multiplexing. So let's talk about frequency division multiplexing. The frequency division multiplexing is the most commonly or the heavily used, and it is actually familiar to anyone who ever has used a radio. Example is your FM radio, which you normally use or listen to in your homes or while traveling in the cars, and even in the television set. The second is time division multiplexing. It is also called as synchronous TDM. So we are going to talk about these two techniques in detail in this chapter. So frequency division multiplexing. As the name suggests, the different input signals, they are multiplexed or combined based on their frequency. That means the different signals, for example, I have a sender 1, sender 2, sender 3. They have data to send, but their signals are having the different frequency. So in this case, frequency division multiplexing, the signals having different frequency but the same wavelength and the same phase will be combined together. That means the signals have a different frequency range now. So frequency division multiplexing is possible when useful bandwidth of the transmission medium exceeds the required bandwidth of the signals to be transmitted. So in this case, the signals are multiplexed according to the frequency. So if you see over here, I have a channel 1 which sends the signals at some frequency X. Channel 2 is sending the signals at another frequency Y. Channel 3 at another frequency. So all these channels, they are sending the signals of the data at different frequencies. So these can be combined together. When these are combined together or the multiplexed together, the technique is called as the frequency division multiplexing. So frequency division multiplexing can be used with the analog signals. A number of signals are carried simultaneously on the same medium by allocating to each signal a different frequency band. So most important point over here is that the signals are transmitted over the shared medium and each signal is given a different frequency band. Number of signals that can be carried simultaneously if each signal is modulated on a different carrier frequency and the carrier frequencies are sufficiently separated that the bandwidths of the signals do not significantly overlap. So in this case, many number of signals can be carried simultaneously, and each signal has to be given and each signal has a different frequency and the carrier frequency are separated. So we have two concepts over here. One is the frequency of the signal of the user. Another is the carrier frequency. So this signal will be carried by some other signal. So the signal which carries our signal from the user is called as the carrier frequency wave. So to say it as more precisely, FDM is possible when the useful bandwidth, as I said earlier, of the transmission medium of the link exceeds the required bandwidth of the signals to be transmitted. A number of signals can be carried at the same time if each signal is modulated on a different carrier frequency, and the carrier frequency, they are separated from the bandwidth. So we are going to talk about, look into the frequency division multiplexing in the next slide. Alright, so moving ahead. So this is an example of the FDM process, how it is done. So for example, in this case, I have a user 1, I have a user 2, I have a user 3 on the sender side. Now this is the frequency of the signal. This is the frequency of the signal, and this is the frequency of the signal. So this signal will be imposed on some carrier frequency wave. So something that will take, because we need a carrier also. So it will be imposed on the carrier frequency 1. Suppose it has a carrier frequency wave which has a frequency 2 and it has a frequency 3. These are of different frequencies. So when these are combined together, the resultant frequency for the user 1 is this, user 2 is this, and the user 3 is this. So if you see over here, there are three different signals from three different users having the different frequency. Now these are combined together and they form a wave something like this. At this point, this is called as multiplexing. Now if you see, when these signals are combined together, this is called as multiplexing. So a multiplexer or a modulator, multiplexer will be used on the sender side. Now at the receiver side, what we have at the receiver side, we have something opposite. We have the filters. Now what these filters will do, these will separate the different signals. These will separate the signals having different frequency. So we will have this filter will take this signal and separate out the signals having the different frequencies. So we have frequency for user 1, a signal for user 2, and signal for user 3. Now the next point over at the receiver end is to separate the carrier frequency and the user frequency. So to separate it, we use a demodulator. So carrier frequency gets separate and user frequency gets separate. This is called as demultiplexing. So this process over here, when we use the filter to separate out the signals having the different frequency, this is called as the demultiplexing. So this is the demultiplexing. So moving ahead, in the case of digital input signals must be passed through modems to be converted to the analog. It is used in TV cable, used in cell phones, used in radio broadcast. So more precise overview of the FDM is given over here. So before we discuss this slide, let's talk about some other important terms. Let me go back to this diagram, right. So in this diagram, what is shown over here, a general case of multiplexing, frequency division multiplexing is shown over here. So if you can see over here, there are 6 signal sources from 6 different senders. They are fed into they are sent to the multiplexer, and with multiplexer modulates each signal on a different frequency. It can be any frequency, frequency 1, frequency 2, and each modulated signal, if you see each modulated signal over here, each modulated signal requires a certain bandwidth centered on its own carrier frequency, and that is referred to as a channel. So each signal that has been modulated, it requires its own bandwidth, which is called as channel. And to prevent the interference, the channels are separated by the guard bands, which are unused portions of the spectrum. So if you see over here, between each channel, there is a dark black line. So what is the purpose of this dark black line? This dark black line actually separates the channel 1 and channel 2 from being interfering with each other. So this dark black line between the two channels is called as the guard band. This is a guard band. Now the purpose of this guard band is to prevent the interference of the frequencies of two adjacent channels. So for example, this is a signal of frequency 1. It is sent using its own channel, and it is sent using its own channel 2. Now channel 1 and channel 2, they are separated by some frequency that is called as guard band. Now this is the unused portion. Imagine a situation, for example, if this signal is sent. Now a second signal has to be sent. If we don't have some separation between the two channels, the signals will overlap with each other. And imagine in the case of FM radio, which you normally listen in your car or at your homes, if two stations are mixed together, just imagine what information or what voices you will be hearing. So that's why the stations are separated by a guard band, and the guard band is the unused frequency. Some frequency is given to this band, but that is not used. That is called as the unused frequency. So to prevent interference, the channels are separated by guard bands, which are unused portions of the spectrum. Composite signal which can be transmitted across the medium. It can be analog. And the input signals can be either digital or analog. So in case of digital input, the input signals must be passed through modem to be converted to analog, and in either case each input analog signal should be modulated to move it to the appropriate frequency band. Alright, so next we move to the diagram that we were supposed to discuss over here. Alright, so this diagram actually shows the frequency division multiplexing in a more detailed over here. So we have many these M1, M2, MT. What are these? These are the signals. So these are the analog or digital signals. These can be the analog or the digital signals. Now these signals have certain frequency, and these signals are to be multiplexed onto some transmission medium. So each signal M1, M2, M3, each signal is modulated onto a carrier frequency Fi. So each signal will be it may have some carrier frequency F1, F2, F3, F4. So M1 is modulated using carrier frequency M1, M2 is modulated using carrier frequency F2, and similarly F1. So F3, Fn or F3. Why? Because multiple carriers are to be used and each is referred to as subcarrier. So these are called as now subcarrier. Any type of modulation may be used. So any type of modulation can be used. We have different types of modulation techniques also. So what is the resulting signal here? What do we have the resulting signal? The resulting analog modulated signal are then summed to produce the composite baseband signal. So after this we will have some signal, after this we will have some signal, after this we will have some signal. So these signals are added together to produce a summed up baseband signal. So the signal that will be produced by combining all these modulated signals will be called as the baseband signal. Now why it is called as the baseband signal? Because it is used to designate the band of frequency, because this signal which we have now has a range of frequencies of the signal to be delivered by the source and used as a modulating signal. So this signal actually consists of signals of many frequencies. So this was a diagram at the transmitter side or at the sender side. Okay, now so what happens at the receiver side? We will talk over here again. So the analog signals may be transmitted over the suitable medium, and at the receiving end the FDM signal is demodulated to retrieve MBT, and it is passed through n band pass filters, each having a frequency Fi. Now if you see over here, this signal is passed through the transmission medium. At the receiver side, this ST signal is received. Now this ST signal is passed through the main receiver and it produces the signal MBT, which was over here. Now this MBT signal is passed through the band pass filters having the different frequency so as to produce the signals with the carrier waves S1T over here like this. And then these signals along with their carrier waves, they are passed through the demodulators, and this after passing through the demodulators, it will produce the signals having the different frequencies which is delivered to the respective receivers. So they have the bandwidth, the BI, it can be in the range of 1 to n. So in this way the signal is again split up into component parts, and each component is then demodulated to recover the original signal. So here the original signal is recovered. So this is how demultiplexing happens at the receiving side. So moving ahead. Alright, now let's talk about guard bands. Do we really need guard bands? So in this figure, there is no guard bands which may cause overlapping. Guard bands are actually used to prevent the overlapping of the signals. So if we don't have the guard bands, the different signals will overlap each other and we will not be able to we will not be able to get what is being there in the signal, or we will not be able to make it out of from the signal, make the data correctly out of it. So that's why we need the guard bands. Moving ahead, now we are going to talk about how to calculate the bandwidth of a multiplex channel using the frequency division multiplexing. As we know, going ahead now, see over here, for example, this is a frequency of the first channel. Now this portion, in between this portion will be some unused portion, but this portion will have frequency. The purpose of this portion is to separate the signals from the two sources so that they do not overlap with each other. Now, how to calculate the bandwidth for the frequency division multiplexing, because we have the voice channels and we have the guard bands also. So let's have an example over here. For example, you are given 5 voice channels, each with the 4 kilohertz bandwidth. Now let me draw over here. So you are given 5 voice channels, each with a 4 kilohertz bandwidth. So for example, I have like this. I have 5 voice channels. This is the first voice channel. This is the second voice channel. This is the third voice channel. This is the fourth voice channel. And this is the fifth voice channel. So I have 5 voice channel, each with a 4 kilohertz bandwidth. What is the bandwidth of this? 4 kilohertz, 4 kilohertz, 4 kilohertz, 4 kilohertz and 4 kilohertz. Now there is a need, we will read it at the later. There is a need for a guard band of 2 kilohertz between the channels. So let me just name the channels. This is channel 1. This is channel 2, this is channel 3, this is channel 4 and this is channel 5. So in between the channels we need to have a guard band. Alright, so that means over here I should have a guard band. Okay. Okay, so going back, so in between the channels, for example here I need to have a guard band. That means and the frequency of the guard band is 2 kilohertz. That means it is 2 kilohertz. In between channel 1 and 2. In between channel 2 and 3, I must have again a guard band, and the frequency of this guard band is 2 kilohertz. In between channel 3 and 4, I must have a guard band, and the frequency of this guard band is 2 kilohertz. In between channel 4 and 5, I must have a guard band, and the frequency of this guard band is 2 kilohertz. So now, how many channels, voice channels I have? I have 5 voice channels. And number of guard bands I have 4. 1, 2, 3, 4. So always remember that we will have the number of guard bands is 1 less than the number of voice channels given. So if you see over here, we have 5 voice channels, but number of guard bands we require is 4. Now how to calculate the bandwidth? Here now, what is the question? We have to calculate the bandwidth over here. Alright, so how to calculate the bandwidth? We will calculate the bandwidth. First of all, we have the 5 voice channels multiplied by what is their bandwidth? Their bandwidth is 4 kilohertz. So 5 channels multiplied by 4 kilohertz plus number of guard bands. We have 4 guard bands. I have 4 guard bands, and the frequency of each guard band is 2 kilohertz. So 2K. When I calculate 5 into 4 is 20K, 20 kilohertz, and 4 into 2 is 8 kilohertz. So the total is 28 kilohertz. Now, when I say draw it, you need to draw like this, the way I have shown over here in the slides. And you need to mention that this is the voice band and this is the guard band. So this is how you can draw it. 5 voice channels, each with 3 kilohertz bandwidth, are to be multiplexed together. There is a need for a guard band of 1.5 kilohertz. So what is the bandwidth? So I have 5 voice channels. Let me draw over here. I have 5 voice channels. 1, 2, 3, 4 and 5. I have 1, 2, 3, 4 and 5. These are the voice channels. And what is their bandwidth? 3 kilohertz, 3 kilohertz and 3 kilohertz. There is a need for a guard band of 1.5 kilohertz. So number of guard bands, I explained in the previous slides that number of guard bands will be 1 less than the number of voice channels. So if I have 5 voice channels, I need 4 guard bands. So this is the first guard band between channel 1 and 2, then between channel 2 and 3, then between channel 3 and 4, and then channel 4 and 5. And what is the bandwidth? It is 1.5, 1.5, 1.5 and 1.5. So let's calculate. So I have 5 voice channels. I have 5 voice channels, and the bandwidth of each voice channel is 3 kilohertz, 3K, plus I have 4 guard bands multiplied by each of it is having a frequency of 1.5K. So 1.5K. When I calculate it, I get 5 multiplied by 3 is 15K plus 4 multiplied by 1.5 is 6K, 6.0K. And hence the answer is 15 plus 6 is 21 kilohertz. So the total bandwidth that is required for this example is 21 kilohertz. Let's check. If you see the diagram is given over here, and how to draw it you can check from here. Okay, now let's talk about analog signals hierarchy. So let's talk about analog signal hierarchy in this slide. Alright, analog signal hierarchy is used by AT&T. It's a long distance carrier system which is provided in the US and throughout the world to transmit the voice band channels over the high capacity transmission link. So the normal telephones that we use in our homes, and the links that are used in the transmission are coaxial cables or the microwave systems. The earliest and still very common technique for utilizing high capacity links is frequency division multiplexing. So in the United States, AT&T has designed hierarchy for the frequency division multiplexing schemes to accommodate transmission of various capacities. So how does this hierarchy works? It has been designed into different hierarchies. So at the first level of the hierarchy, this is the first level of the hierarchy. There are 12 voice channels, and the bandwidth of each voice channel is 4 kilohertz. So these are 12 voice channels, and the bandwidth of each voice channel is 4 kilohertz. So total bandwidth is 48 kilohertz. And it is in the range of 60 to 108 kilohertz. Alright, and it is in the increments of 4 kilohertz. And the next basic building block is the 60 channel supergroup. So we have the 60 channel supergroup. So there are 60 channels in this supergroup, which is formed by the frequency division multiplexing of 5 group signals. So at this group, each group is treated as a single signal with a 48 kilohertz bandwidth and is modulated by a subcarrier. So the subcarriers may have the frequency between 420 to 612 kilohertz and in the increments of 48 kilohertz. So what does this mean? That it means in the first hierarchy we have only less number of voice channels. In the second hierarchy, there are 60 voice channels and the total bandwidth is 240 kilohertz. And in the third hierarchy, there are 600 voice channels and the total bandwidth is 2.52 megahertz. And in the last group, there are 3600 voice channels, 6 master groups, and the bandwidth is 16.984 megahertz. So this is actually the hierarchy which is offered by the AT&T. Now we will talk about, that was all about the frequency division multiplexing. So now we are going to talk about the time division multiplexing. So time division multiplexing, it's a digital multiplexing technique. Frequency division multiplexing is an analog multiplexing technique. So it's a digital multiplexing technique for combining several low rate channels into a high rate channel at a specific time. So what happens in the time division, in the frequency division multiplexing, the channels are multiplexed, the channels that are multiplexed have different frequencies. But here in the time division multiplexing, the channels that are multiplexed, they are allocated different time. So it's a quite different type of multiplexing technique. We have synchronous division multiplexing also, but we will talk about it later. So let's understand the basic idea regarding the time division multiplexing. Now in the time division multiplexing, suppose we have n users and they are connected to the receivers by the single transmission medium. Now this transmission medium has to be shared among all these senders. So what happens is this medium is shared among the users not according to the frequency but according to the time. So how it is shared according to the time? So for example, the user 1 will be allocated time to send it frame. Suppose it has 1 frame to send, it sends the 1 frame. Then after this, user 2nd will be given the time, user 2nd send its frame, then user 3rd send its frame, and then user 4th send its frame. Then again this process will be repeated unless all the data all the users have been sent. So now user 1 will send again, then user 2, then user 3 and user 4, and then again user 1 its turns come again, then user 2, user 3 and user 4. So this is how the time division multiplexing is followed. So in time division multiplexing, each user is given a time to use the shared transmission medium so as to send the data instead of using the frequency. Now at demultiplexing, when this is received, so suppose for example this is frame 1. When this frame is received, this will be a first frame, this will be combined as one. This will be a second frame, or we can say group, and this will be the third group. So when this first group is received, this demultiplex will separate out. So it will send this first frame to the first receiver, second frame to the second receiver, third frame to the third receiver, and fourth frame to the fourth receiver. This is actually you can say efficient multiplexing technique which is used in the modern day industry today, and we will explore more about it. So time division multiplexing. So if you see over here, time division multiplexing is depicted over here in this figure. So multiple digital signals or even the analog signals, they can be carried into the same transmission path by interleaving portion of each signal in time. So the signals are interleaved. The interleaving can be at the bit level or in the blocks or bytes for the larger quantities. So for example, suppose there are 6 channels, so channel 1 is given the time, channel 2, channel 3, 4, 5, 6, and then so on. This process carries on. Now we talk about synchronous time division multiplexing. It's a type of time division multiplexing. So synchronous time division multiplexing can be used with digital signals or with the analog signals which carry the digital data. So in this form of multiplexing, data from the various sources can be carried in the repetitive frames. This is what I showed. So repetition of frames is there. Each frame consists of a set of time slots, and each source is assigned one or more time slots per frame. So each source is given a time slot. Synchronous TDM, it is called as synchronous not because of synchronous transmission, but because the time slots are pre-assigned to the sources and it is fixed. So each user has a fixed and a pre-time time slot. That's why it is called as synchronous. Now, the time slots for each source are transmitted whether or not the source has data to send. So, for example, if I go back in this previous example, suppose at this point, user 2 does not have any data to send. So, what will happen? Still, this time will be assigned to the user 2 even though the user 2 does not have any data to send. This is called as synchronous time division multiplexing. So this is used in T1, ISDN, SONET and SDH. Synchronous time division is possible when the achievable data rate of the medium exceeds the data rate of the digital signals to be transmitted. And in this case, multiple digital signals can be carried on a single transmission path by interleaving the portions of each signal in time. And a single line with a capacity of at least 6 Mbps can accommodate the 6 sources. So this is a quite new technique. Alright, so if you see over here in the synchronous time division multiplexing, if I explain over here, suppose there are 3 users, A, B and C. A has 3 frames to send, B has 3 frames to send, and C has 3 frames to send. So data will be taken from each of the user at every time interval. So when time t is equals to 1, A will send its first frame. When time t is equals to 2, B will send the first frame. When time t is equals to 3, C will send the first frame. So this will make a group, a common group carrying the first data or the first packet from each user. Then when time t is equals to 4, A will send its second packet. Time t is equals to 5, B will send, and then time t is equals to 6, C will send. So this will make the second group. When time t is equals to 7, A will send its third frame. Time t is equals to 8, B will send its third frame, and time t is equals to 9, C will send its third frame. So this will make the third group. Each frame is 3 time slots and each time slot duration is t/3 seconds. So this is an example of the synchronous TDM system overview. Let's understand it. How does it happens? So let's understand this diagram. Now this is a depiction of the synchronous time division multiplexing. Now this upper part shows how the data is sent from the sender side, and the lower part shows how the data is received as receiver side, and this talks about the frame. It may be empty or it may be occupied, about the TDM frames. Alright, so let's first of all start with the transmission part, and then we will discuss with the receiver part. So a number of signals, signal means number of sources are to be multiplexed on the same transmission medium. So the basic idea, whether it's frequency division multiplexing, wavelength division multiplexing, or any kind of multiplexing, the basic idea is the same, that we need to combine the signals from different resources. So a number of signals, so suppose first user, the signal is M1, M2 and M3. So these are multiplexed onto the same transmission medium. The signals carry digital data and are generally digital signals. Normally in case of time division multiplexing, the signals that are generated are digital signals. The incoming data from each source are briefly buffered. So whatever the data the user is sending, it is buffered. Now what is a buffer? Buffer is a temporary memory location for storing the data temporarily. So it's a temporary memory location for storing the user's data. The buffers are scanned sequentially to form a composite digital data stream. Now when these signals are saved in the buffer, now these are scanned and they are then combined to form a digital data stream, which is called as the combined signals from each of the resources. So the scan operation is sufficiently so rapid that each buffer is emptied before more data can arrive. This scanning operation is quickly, within a blink of the eye. So thus the data rate of the combined signal stream must be at least equal to the sum of the data rates of the MIT. That means the combination of these signals. So the digital signals that we have scanned and combined may be transmitted directly through a modem, so that analog signal is transmitted, and in either case transmission is typically synchronous. So now this combined signal is passed through the modem. So this was all about the sender side. So the transmitted data may have a format, something like over here. When this data is transmitted, this transmitted data will be in the form of frames, like this shown over here. So the data is organized into frames, and each frame contains a cycle of time slots, and in each frame one or more slots is dedicated to each data source. So each user or each data source has a time slot dedicated for it. The sequence of slots dedicated to one source from frame to frame is called as the channel, and the slot length equals to the transmitter buffer length. Typically it is in the size of the bytes. So it is in the size of the bytes. So the bit interleaving technique is used. What is bit interleaving? That means first bit from source 1, first bit from source 2, first bit from source 3. Then second bit from source 1, second bit from source 2, second bit from source 3, and so on. This is called as the bit interleaving technique. So bit interleaving technique is used for making out the frames. Now what happens at the receiver end? At the receiver end, this modulated time division multiplexed stream is received. So it is demultiplexed and routed to the appropriate destination buffer. So it is passed through the it is demultiplexed. For each input source, there is identical output destination that will receive the output data at the same rate. So at the receiver end, the opposite operation is formed. This signal is received, sent to the modem. It will result in the combined data stream, and then it will do the scanning of this combined data stream and generate the individual signals, send it to their respective buffers, and then the individual signals will be retrieved and then sent to the sender. So synchronous TDM is called synchronous not because synchronous transmission is used, because Time slots are pre-designed to the sources. So the time slots for each source are transmitted whether or not the source has data to send. So each source will have a time whether or not the source has a data to send. So more on summing up the time division multiplexing. It's a digital multiplexing technique to combine the data. It has a medium data rate, signal data rate. Multiple digital signals are interleaved in time. Interleaved means first of all first bit from A, B and C, then from A, B and C. So this is how interleaving principle works. Time slots are pre-assigned to the source and fixed. And time slots are assigned to the sources even if the sources they do not have the data to send. Do not have to be evenly distributed among the sources. So just a conceptual view of TDM. So in the time division multiplexing, we have we need to multiplex the signals based on time. So we will do the interleaving of the bits. So first we take the bit 1 from user 1, then bit 1 from user 2, and then bit 1 from user 3. We make a group out of it. Then we do the same thing, then we do the same thing. So when it is sent at the receiver side, these are multiplexed. Bit 1 is sent to the receiver 1, bit 2 is sent to the receiver 2, and bit 3 is sent to the receiver 3. So this is all about for this lecture, and more on time division multiplexing we will discuss in the part 2 of this lecture. So thank you so much.